Okay, our recording. So let me start again. So the chapter title is Torque and Equilibrium. So we'll see what this torque means, and we bring back equilibrium again. These are the content, table of content. So first topic is force and extended object. So torque is to not circular movement. We will talk about torque. Okay, let's be patient. So we will go slowly. So the topics are the first one, force and extended object. We learned force before, but we are bringing back again because this time we will see what happened when you apply a force and extended object. All objects are extended, but so far we kind of ignored the size of an object. We reduce all the object to a point. So we draw the free body diagram. I mean, thinking any object is reduced to a point and all the forces are applied at that point. So the size doesn't matter, but we cannot do it anymore. In reality, objects have sizes, and where the force is applied is going to matter. So depending on the application of the force, the way that object behave or move will differ. Okay, is that clear? Now, and in number 2, we introduce what is called torque. Torque, I can say, approximately, that is the turning effect of a force. So we have a force, depending on where the force is applied, it can not only move it linearly, it can even start rotating it, spinning it about a fixed axis. Okay, so that is why we need to define this new thing called torque. Section 3, we bring back the equilibrium, but this time we will consider rotational motion as well, because the torque or the turning effect of the force, which is the torque, will start rotating the object. So complete equilibrium will be when the object not only moving linearly, but also not rotating even with about a fixed axis. And good morning. And then the last topic that we will be covering is levers. Okay, lever arm and physiological application in biology and life sciences. The last 2 topics here are omitted, so we will make it easy for us. Right, let's start. Now we see here on the left-hand side, 3 forces are applied on an object. And we have those 3 forces. The net force, if we add those 3 forces, we have 0 force. Okay. So that means, if you remember what we learned before, if the net force is 0, there will be no acceleration. So that means it is in equilibrium. So if it has a 0 velocity, it will continue to have 0 velocity. So that's the case on the top figure A. So these forces are balanced, because if you add them, it adds up to 0. So it is not going to move. If it is not moving before 0 velocity, it will continue to be at 0 velocity. Okay, and now this time something strange happened. We take the same 3 forces, exactly the same. Say, here also, the forces, same forces, but we apply in a different manner. There is a difference between the top figure and the low figure. What do you think is the difference? The same 3 forces, but in A, yeah, very good. So in A, the forces meeting at one point, okay, but in B, the forces are not concurrent. See, the term is concurrent, mean they're meeting in one point. But here in B, they are not meeting at the same point. So we call it non-concurrent forces. Now, when that happens, this time in B, the object is not in equilibrium. What do you think will happen? It will start spinning. Okay. The center of mass of this object, let's say if it is here, that point will not spin, but everything else will spin around that point. So it will do a rotation motion depending on which direction it is rotate more. That those forces will have a turning effect on this object. So although it is not going anywhere, the center of mass will be fixed in one place, but it's going to start spinning around that center of mass. So now you see why rotational motion is important. Just because the extended body has a size, where you apply the force is important. In here in A, it is the same three forces, but we apply it concurrent way. So there's a common intersection. It is not moving, not even rotating. But in B, because where the forces are applied and the forces are not concurrent, there will be rotation. So it is not in equilibrium. Although it is, what we call translational equilibrium, but it is not in rotational equilibrium. There is rotated motion. This can be, even more clear if you look at the other example on the right. So let's say we have a rod placed on a smooth, frictionless table looking from above. Let's say you apply a force of 10 Newton down and okay, well, one direction, and another force also 10 Newton in the opposite direction. It is the same thing here, same two forces. Now you know what's happening here. In the top figure, it will be not moving, complete equilibrium. There is not even rotation. But in here, it will start moving around, right? Because the forces are not concurrent. So where the force is applied is important in an extended object. All the objects we have are extended, they are not point, okay? But so far we kind of ignored this, but we cannot do it anymore. Now we have to consider the rotational motion as well. So we are putting the foundation for how to deal with rotational motion. Okay. Force an extended object. Now we looked at the extended object. And also we will make sure that extended object is a rigid object. So now we need to know what we mean by rigid object. Very simply, I can take two examples. So we take a solid rock or a stone, and we take a jelly. The jelly is wobbling, right? It is still a solid, but it is not a rigid object. Air, fluid, and water, those are not rigid objects. Even solids like jello, the solid can be non-rigid. What is the definition of rigidity? Say, suppose we take an object and take 2 points in that object, A, B. The distance between A, B will remain fixed with time for a rigid object. If it is not a rigid object, it can change, like a wobbling in a jelly. Additionally, we also need to require another thing. Take 3 points, A, B, and C. The angles between these 3 points, 3 lines, the lines connecting these 3 points are also fixed. So if it is 30 degrees, say 60 degrees, and 30 degrees, they will remain the same angle. So if these conditions are satisfied, these 2 conditions are satisfied, we are happy it is a rigid body. Why we bother, defining it? Because, if you move to non-rigid body, it becomes complicated. So we want to start slowly, simple. Okay, so we'll keep it simple. So we will apply the dynamics or the Newton's second law for extended object, but only rigid extended object. Okay. So now there's a question, Saad. So A is in equilibrium, B is not in equilibrium. Yes. Yeah, you are referring to the previous. Yeah, because the 1B below, the forces are non-concurrent. So where the force is applied is important. It will produce rotation, spinning. That's why it is not in equilibrium. So we are putting the foundation to study rotational motion. So to study rotational motion, this concept called torque is important. It has something to do with the force. The turning effect of the force is called torque. Okay, so we will see. We will slowly introduce this concept. Then we will give a mathematical, precise definition. Torque produces rotational acceleration because we knew before force produces acceleration. That's a Newton's second law, right? But there, translation only linear. We reduce everything to a point, so there can't be any rotation for a point, right? So we only talk about linear motion or translational motion. But we cannot do that anymore. Now we have to deal with the real life things. Things in real life have size. So where the force is applied is going to matter. It will start rotating the object depending on whether the forces are concurrent or non-concurrent. So the torque, like the forces produce translational acceleration, torque, which is related to the force, okay? Any force, we're going to have a torque depending on where the force is applied. That torque produces rotational acceleration. If it is not rotating, it will start making it rotate. So it's an acceleration. So now to introduce this torque, we have this very nice example. This is what is called miniature seesaw. Okay, this in the playground, you have this thing, people sit on either side and you go seesaw. Okay, that is seesaw. Okay, now this seesaw, it is balanced initially, nothing on it. And in B, figure B, we keep two masses on either side of it, same mass, equal mass, and at equal distance from the hinge. Hinge is where it can turn in the middle. It will be in balance, right? If we keep equal masses either side, it will be in equilibrium. Okay. Now in C, what we do, we put a bigger mass on the right-hand side. I draw it big. You know what will happen? The force, the weight from the bigger mass will have a bigger turning effect compared to the smaller weight. The forces are now not the same. Force is the weight of the object. And at B, we have a big force, the gravitational force. Therefore, the turning effect from B will be greater compared to the turning effect from A. So it will rotate to the counterclockwise more than, this clockwise. This is clockwise rotation is more than the counterclockwise rotational force from B. So that's clear. Now, what about D? What we do differently? Now in D, we keep at the same, this is why it is more, because the weight is more. It is the same distance from the hinge. Now here, in D, no, I'm sorry, I said the wrong thing. It is not different mass. Okay, B is not different mass. It is the same mass. Okay, it is the same mass. Same mass. Let me read, with equal mass. But what's the difference here? The distance on the right-hand side is bigger than the distance on the left-hand side. here we have the same mass, here also we have the same mass, but the rotation effect from the right hand side mass is greater than the turning effect from the left hand side. The reason is it is kept far from the hinge. Okay, is that clear? It's clear, right? People online, are you listening? In C, we have equal masses on either side of the hinge. Hinge means the central where it can rotate. Let's not introduce any term, okay, fine, because we are learning. We are going to assume maybe that term we will not use it at all, okay? So I'm simply asking you, in C, why we have equal mass, but the right side mass is having more turning effect compared to the left side force, okay, the mass. The reason is the distance away from the hinge point, right? Okay. Let's look at D. In D, we have the same distance, but this time the forces are different. We keep this is the big and opposite, this is the small. So yeah, so you can see the turning effect depends on the force as well as the distance to the force. So where the force is applied does matter. So now this is, we are laying the foundation for the talk to understand conceptually what the torque means. Torque is the turning effect of the force. So the turning effect of the force, we can see depend on the weight, I mean the force itself, magnitude of the force, and it also depend on the distance to the force from the rotation axis. Now, what about E? What we have in E, they are two unequal masses. Okay, this is a big mass, the same thing. But this guy, small mass, but it is away further from the hinge point. So the smaller force is kind of offset by bigger distance. Now I'm going to open a website where we can do simulation, and it is a lot of fun. You can play with that and learn at the same time. Let me open this. Yeah, the factors in the torque is the force, not just mass, because it's proportional to the mass, because the gravitational force, right, that is, we are seeing that particular force is the gravitational force. Gravitational force is mass into gravitational acceleration, which is a constant. So you can say it is, but you have to say it correctly. You should say the torque has something to do with the force and also the distance from where the force is applied, distance from the rotation axis. So we have a very nice demonstration here. Now we have a seesaw, and let's say we keep the 5 kilograms somewhere here, and the other 5 kilogram also the same distance, say 1, 2, 3, 4. Now it should be balanced, right? When we take out the support, it is balanced. Let me show the level and force from the object. Okay, things are balanced. Now let's do this. Now, what if I move this away to here? It is not balanced. The turning effect from the 5 kilogram is greater on the right-hand side because the distance is away. So the turning effect depends on the where the force is applied. The force is applied far from the rotation axis, so the effect of the turning effect is greater for the force on the right. Okay, now I'm going to balance this guy. You can either move this guy here, so now it will be balanced. That is one way of balancing it. Or let me keep it back and take him out and use the 10 kilogram at the same place as before. It will be balanced, right? Oops. You see, now if you count, this is 1, 2. 2 into 10 is 20. Here 5. 5 into 1, 2, 3, 4. 5 into 4 is also 20. So the torque, if you are going to define the torque, it seems to be, it is the force multiplied by the distance. That is the torque. So on the right-hand side, we have a, when you keep this side, it is trying to turn it clockwise, right? So the torque from the right-hand side is a clockwise torque, and the torque from this guy is trying to turn counterclockwise. So we can say counterclockwise torque. So you can have, for a fixed axis of rotation or turning, two direction, counterclockwise and clockwise. So we can do all this experiment, with this simulation, kind of a virtual lab. And there is a very nice games also. You can. Okay, for example, say we keep, this is a gift of some unknown weight. We can find its weight by, trying other masses and see whether it is balancing or not. Suppose we guess it is 10 kilogram. So if we keep this 10 kilogram at the same place as that one, should balance. So it is not. So that means the distances are balanced both sides. It is on the same distance, right side and the left side. So that means A must be heavier than 10 kilogram. So we don't know. We can move this guy away. So now see, looks like it is even more than that. So now it is 10 into 3, 30. Here, something into 2, we don't know what it is. So let me move it there and see if it's balancing. Now, can you guess the mass of this A? We will say 10 multiplied by 1, 2, 3, 4, 40, right? The torque effect from the right side is 40. And here, multiply by 2, right? 1, 2. So A multiplied by 2 must be equal to 10 multiplied by 4. So 40 must be equal to 2A. That means A is equal to 20. Okay, so we get, so you can find the weight of that by applying the principle that we've just learned. The turning effect. The torque should be equal either side. This is a what we call clockwise torque from this guy, and this is a counterclockwise torque. So the two torques, if they become equal, the net counterclockwise torque is equal to the net clockwise torque, the thing is going to be balanced about the rotation axis. If it is equal, it will be balanced. Okay, so here, now we know it is balanced. That means the torque should be equal, because this is counterclockwise and that one is left side is counterclockwise. So we will say A multiplied by 2 must be equal to 10 multiplied by 4. So that gives me A is equal to 20. Okay, right. So that's, you can, I have given the link there, so you can play with that on your own time. So let's move on. Now let's define it properly, mathematically, what this torque is exactly equal to. Okay. Consider a force F acting on a bar that can rotate freely around a fixed axis. If the force applied on the bar at a distance r from the axis of rotation where it is free to rotate, and at an angle theta, let me draw a picture for that. Say it is free to rotate about this point, and you apply a force F, and this is the distance r. Let me take as a vector, a line drawn from the rotation axis to where the force is applied, that is r, and the angle between r and theta, r and f is theta. Then we say the torque equal to, we use the symbol Greek letter tau for the torque, is equal to the r, which is the distance to where the force is applied from the axis of rotation, multiplied by magnitude of the force, multiplied by sine of the angle between r and f. What is theta? Theta is the angle between the vector r and the vector f. So we can now group these two together and say this f sine theta is none other than the perpendicular component of f. Perpendicular to what? Perpendicular to the vector r. So you can write for the f sine theta, we can put this, and we'll say the magnitude of the torque is equal to the distance to where the force is applied from the axis of rotation, multiplied by the perpendicular component of the force. Okay, that's, you can just simply say RF sine theta and substitute the value of magnitude R, magnitude F, and the sine of the angle theta, or you just take the R and multiply by the perpendicular component F. They are both the same. What about the unit for this? It will be force is Newton and the distance is meter. Sine theta has no unit, so it will be Newton meter. The unit for the torque, SI unit is Newton meter. For Newton, you can also, Newton is actually kilogram meter per second squared. So that will be kilogram meter squared second squared per second squared. So now we have defined mathematically precisely what is this torque. So here is the figure that's showing it again. So this is where it can rotate and the force is applied here. So this will be the R with the arrow going from the axis of rotation to where the force is applied, and say it is making an angle of theta with R. Then this is the perpendicular component and this is the parallel component. We resolve the forces along R, that is the parallel component. We resolve the force perpendicular to R, that is a perpendicular component, and the torque magnitude is equal to R F perpendicular. Okay, now we can check our understanding, how much we understood by answering this question. Okay, easy question, but a really a good question. It really tells you how much you understood. In the following slide shows different configurations where a force is applied on a uniform bar that can rotate freely around an axis. And the dots represent the axis of rotation, and the force arrows all have the same length. Which of these configuration will produce the largest torque? Okay, let's look at the picture. Okay, here it is. We have A, B, C, D, E. 5 configuration. The forces all have the same magnitude, same length in all 5 configuration, but they are applied at different places and also different angle. Right. So let me start with A. Knowing what is the torque? The black dot represents where the rotation axis is. We need to rotate about the black dot. So it is fixed to the black dot. That is where the rod is fixed. So it can rotate freely around that black dot. In figure A, what is the torque? Equal to. It is balanced, you mean? Now equal to what? The torque from that force. Torque is given by this, right? R, F, sine theta. F is this. Theta, can you say anything about theta? What about R? Let's me look at R. What is the definition of R? Distance, the distance where the force is applied. Distance from what? To the axis of rotation, from the black dot, which is where the rotation axis, to where the force is applied. So R equal to what in A? 0. Oh yeah, very good, Kazi. See, dot and where the force is applied is the same place. The black dot and where the force is applied is the same place. That means R is equal to 0. So the torque in figure A is 0. It doesn't matter how big that force is. Can you turn that thing by applying the force at the point? No. So the torque from that force, no matter whatever, how big it is 0. Now let's look at B. R is this. And we know the torque will be only the perpendicular component of the torque. So let me draw the perpendicular component. So this red is the perpendicular component, will contribute to the torque, right? The parallel component will have no effect. So the torque will be perpendicular component multiplied by the blue arrow R. Let me use a black arrow, maybe black for the R. The torque will be the black line multiplied by the red line. Okay. Well, we don't have numbers, so let me leave it there. Let me go to C. For C, this will be the R, right? R is, what is the definition of R? From the black dot, rotation axis, to where the force is applied. Okay. So again, the perpendicular component, let me get the perpendicular component. Let me use red. This is the perpendicular component. So that will be the black line multiplied by the red line, that will be the torque. Obviously, E is greater than D torque, right? Because we have a long black line compared to the short black line there. So how do you get the torque? By multiplying the R and F perpendicular. So obviously C is greater, okay, but let's look at D also. What about D? The black line is again becoming short. And the red line is bigger than the other two, but we don't know, we have not exact numbers, so it's difficult to judge. Okay, maybe still C is greater, we don't know. Okay, let's go to E. Obviously, E is the greatest, right? E is the greatest. So the question is, get the greatest, and E has no contest at all. Obviously, it is the A is 0, the smallest, and B, E, D, we don't even have to bother comparing them. For sure, E is the greatest. So we The question is just to find the greatest torque. So now we have another question. The figure is in the next. There is a bar or a rod raised at an angle of 36 degrees. Find the magnitude and direction of the torque acting on the bar due to a horizontal force of 7 Newton acting at one end. I will quickly draw it here as well. There is a force. I really don't know why it is doing this. Okay. So let's go to the next slide. So this is the bar, and the force is applied here, shown by the green arrow. Okay, I made it red now. All right, now according to the definition of the torque, this is your R multiplied by the perpendicular component. So if this is the original force, the perpendicular component will be this, which is F sine theta, because this angle is theta. If this is theta, that angle between R and F is theta. So the perpendicular component will be F sine theta. So we simply have to substitute R F sine theta. We know all the values. R is given to us, F is given to us, theta is given to us. It's a matter of substitution. So we say it is the perpendicular component multiplied by R. So perpendicular component is F sine theta anyway. Now we can also get the torque in a different way by what we call the lever arm. So we can also say that the torque magnitude is equal to R sine theta multiplied by total force, not the perpendicular force. And we call this R sine theta as R perpendicular or the lever arm, or also called the moment arm. Now you can see that lever arm or the perpendicular distance is this. It is by extending the line of force, line of action of the force, and the perpendicular distance of the force to the rotation axis is called the perpendicular or the lever arm or the moment arm, a perpendicular distance from the axis of rotation. It's going to give the same answer because it's a matter of whether you are putting the sine theta with the F or whether you're putting the sine theta with the R. If you group it with the F, you say the torque is equal to R into perpendicular force, or if you group it with the R, you can say the torque is equal to the perpendicular distance multiplied by the total force. Just two ways of looking at the same thing. Whatever you do, you're going to get the same answer. So R is 1.7, force is given as 7 Newton, and theta is given as 36, and you get 7 Newton meter. Now, what about the direction of the force? Torque. Torque has a magnitude, and it also has a direction. It will be either counterclockwise or clockwise. So we have only two directions. Now, for this particular one, we had it like this, right? The force is acting like this. And this is your R. So what direction will it turn this if you push it like that? It is turned counterclockwise. So the direction of the torque is counterclockwise. So you know what is clockwise, counterclockwise, right? The clock hand turns in the clockwise direction. So the other direction is counterclockwise. Right, now, torque is a vector because it has direction. Now we are saying it is counterclockwise direction, clockwise direction. But counterclockwise, clockwise is not a direction, right? Can you say, put your finger and say, look at the clock moving? It is rotating, right? What is its direction? I mean, it is, we cannot say, point with your finger and say that is the direction. So we need to provide a direction for this counterclockwise and clockwise. But anyway, let me write the magnitude first. Okay, we write it in this form as a vector product. I mean, the vector multiplication. This vector R and the vector F, they are both vectors, right? So we call this as a vector multiplication, and the torque is equal to the vector multiplication of these two vectors. Magnitude is given by RF sine theta, which can be either written like this, R into perpendicular force, or perpendicular distance, the lever arm multiplied by the total force. Now the direction is given by what we call the right hand rule. So I want you to pay attention to this picture to understand this right hand rule. So when you want to get the direction of the torque, you take your right hand, so because do not use your left hand, it's very important, first of all. And then point your fingers, other than the thumb, in the direction of R. First, you have to bring the R and F together. R and F, tail to tail, okay? You have to bring the vector R and vector F tail to tail, okay? It's starting point. Then you point your fingers in the direction of R, the arrow R, and curl the fingers now towards the force F, and the thumb will show the direction of the torque. The direction of the torque will be perpendicular to both R and F. It will be perpendicular to the plane formed by R and F. So it will be either up or down to that plane. So it depends on, okay, you have to move from R to F. Your fingers should curl from R to F through the small angle, okay? Then the thumb will give you the direction of the torque. So this is how we get the direction of the torque using the right hand rule. So, you know, you can see on the right hand side, you have another picture. You can see that vector R and vector F here. And when you turn your, curl your fingers from R to F, the thumb will be pointing up. So looking from above, it is counterclockwise. They also call it anti-clockwise, same as counterclockwise. So don't get confused, right? Counterclockwise and anti-clockwise is the same. But if you look at this one, now here the force R is this, and the force is this. Now this time you need to, you know, keep your curl your finger from R to F. You have to, you know, this time in the figure B on the right hand side, your thumb will be pointing down. Okay, I hope you understand it. Any question, please? Do I need to explain it more? Is it okay? Okay. Let me see online people. Clear. Thank you. Right. Now here we are showing it again on an XY coordinate. Let's say R is along the X-axis and F is along the Y-axis, and the direction of the torque will be along the Z-axis. Now the magnitude of the torque is simply the area, because, you know, it is a right angle, so the angle is 90 degrees. So it's R, F, R is this length, F is this length, multiplied by sine 90. Sine 90 is 1. So that is the area of this. Okay. If it is not 90 degrees, it still will be the area, because that it becomes sine theta. It can be shown that's a parallelogram. The area is given by R of sine theta. Okay, now we have a concept question which we have to take seriously, this one. Someone who reads a physics book too quickly is asked to recall the vector torque equation, but cannot remember the order of the vector R and F. What consequence will this have on the result? Meaning the torque, whether you write it like this or whether you write like this, F first and R next. What is the problem with this one? This is how it is given correctly. R first and then the force. But suppose you forgot that, you forgot the order and you wrote that the torque to be equal to F first and then R. Is it correct? It is not correct, because then the direction will be wrong. Okay, magnitude is fine. Okay, R F sine theta, it will have no effect. But if you write the F first, then the R, what you thought as the if you use the correct equation, suppose you get certain direction with the correct equation. For the incorrect equation, you will get the opposite direction. So that's why the order is important. Another problem is instead of using the right hand, if you use the left hand also, you will get the direction flipped. So it is very important you remember. So you point your right hand fingers along R, not along F, because R come first. Then curl the fingers towards F through the smaller angle. Then the thumb will give you the direction of the torque. And also, if you use the left hand, you will get the opposite result. Okay, I will stop there. We'll continue, take it up from the next class. Okay, any question, please? No question, thank you.